So next one is completeness property of real numbers. And as per statement of completeness property of real numbers, every non-empty set of real numbers that has an upper bound also has a supremum in R. So given any non-empty subset of set of real numbers, if it is bounded above, then completeness property of real number guarantees existence of supremum in real number, and if it is bounded below, then infimum will exist. And in earlier lecture, I have already discussed how to check whether a given set is bounded above or not. If there exists at least one upper bound, then we will say that set is bounded above. And then next, if it is bounded above, then we will collect set of all upper bounds, and the least upper bound from those set is called as supremum. So this one is a very fundamental property which will be used in several proofs. One of the fundamental property which we will use in different proofs. If set is bounded above as well as bounded below, then supremum as well as infimum will exist in R. So let us do question number 1. Continue our discussion with some examples. For sake of explanation, let me explain this one, question number 1. So as per S1 is basically collection of all those real numbers such that x is greater than or equal to 0. So I can write S1 as closed interval 0 to infinity. Now the question is whether this set is bounded above. So this set is not bounded above. Why? Because it has no upper bound. Suppose someone is giving us upper bound, say 100.5. So to discard that this one is not an upper bound, I need to produce at least one member from this set, say 120, which exceeds this 100.5. So in this way, every upper bound, the claim of upper bound will be discarded. So this set is not bounded above. Now whether this set is bounded below? Yes, this set is bounded below. Why? Because 0 is one of its lower bound. 0, if we choose alpha equal to 0, is one of its lower bound. One of its lower bound. So since we have one of the lower bound, so we will say that this set is bound. Why it is one of the lower bound? Because for every x belonging to S1 set, x is greater than or equal to 0, or we can write 0 less than or equal to x, where x belonging to the set S1. So every member is either equal to 0 or right to 0. Hence this set is bounded below. Now, so what will be set of all lower bound? Set of all lower bound. Set of all lower bound is minus infinity to 0. 0 included, because 0 is also one of the lower bound. So infimum, as per definition, infimum is greatest lower bound, and greatest lower bound of this set S1 is 0. Hence its infimum is of the set S1 is 0. So this is the technique we used to prove. We used to do questions to find out infimum, supremum, all. Question number 2, S2 be the set such that x is greater than 0. Does S2 have lower bounds? Yes, S2 have lower bound. 0 is one of the lower bound, because in set form I can write this as, yes, question number 2, solution to question number 2. In set form, I can write S2 as open interval 0 to infinity. So what about this set? Does S2 have lower bound? Yes. Beta is equal to 0 is one of its lower bound. One of its lower bound. Another question, does S2 have upper bounds? No, S2 have no upper bounds, because we will get a real number which will exceed that upper bound, whatever be our claim. So S2 has no upper bound. Does infimum of S2 exist? Yes, infimum of S2 exists. So for that we will use the technique. We will write set of all lower bounds, set of all lower bound, that will be minus infinity to 0, closed at 0, and from the set of all lower bound, infimum or the greatest lower bound GLB of this set S2, that will be equal to 0. So 0 is its lower infimum, and we can see that infimum here is not member of the set. This one is open interval 0, so infimum exists, may or may not be member of the set, and when infimum is the member of the set, we can also refer it as minimum of the set. So minimum of the set whenever exists will be member of the set. Does a supremum of S2 exist? So we have answered this question. Prove your statement. We will come back to this using Archimedean property of real numbers, that I will refer in different section. Here just I am emphasizing that how to compute upper and lower bounds, how to check whether a set is bounded above or not, and if it is bounded above or bounded below as per the case, how to find its supremum and infimum. Let us do question number 5, part A. What we need to do here, find the infimum and supremum if they exist of each of the following sets. So 5A part is basically, A part I can write, this one is the set X belonging to R such that 2x plus 5 is greater than 0, 2x plus 5 is greater than 0. So we need to solve this inequality. This 2x plus 5 greater than 0 implies x is greater than minus 5 by 2. So set A will be all collection of all real numbers greater than minus 5 by 2. So interval form I can write it as open interval minus 5 by 2 to infinity, minus 5 by 2 to infinity. Now clearly this set is not bounded above but bounded below. So one of the lower bound is minus 5 by 2 itself, because for every x belonging to A, minus 5 by 2 is less than equal to x. That is, every x is going to either equal to minus 5 by 2 or exceed minus 5 by 2. Hence minus 5 by 2 is one of the lower bound, and any real number less than minus 5 by 2 is also its lower bound. So set of all lower bound will be minus infinity to minus 5 by 2 and minus closed at minus 5 by 2. So infimum, as per definition, infimum is greatest of the lower bounds, and that is minus 5 by 2. So in this case minus 5 by 2 is its infimum, and supremum will not exist. Why supremum will not exist? Because it is not bounded above. For existence of supremum, first the set has to be bounded above. So A part we have done. Now let us do part C. Similarly one can do part B. Now let me emphasize on this part C on the new page. Part C, 5, part C. I need to find the given set is set C is equal to collection of all those x belonging to set of real numbers such that x is less than 1 by x. This is the set. So first of all we need to solve this set. Clearly this term is defined when x is not equal to 0. So one of the restriction we have on this is x has to be non-zero, x less than 1 by x. Now but since x is non-zero, so we have two cases here. In case x is negative, because on cross multiplying the inequality will reverse if x is negative. So we have to take two cases, x greater than 0 and x less than 0. In case x less than 0, the inequality will reverse. We have x square greater than 1, that is x square minus 1 is greater than 0. In case x is greater than 0, if we multiply by a positive number on both sides, the inequality will be same. So, in this case we have x square minus 1 less than 0 with the condition that x is not equal to 0. Now, let us simplify both cases. So, if we simplify this one, we have x minus 1, x plus 1 less than 0. This implies minus 1 less than x less than 1, or we will get minus 1 to 1. But since x is greater than 0, so if after taking its intersection with such x such that x is greater than 0, and also x has to be non-zero intersection all those x such that x is not equal to 0, we will get the right part of this one 0, that is open interval 0 to 1, open interval 0 to, because we do not have to take x equal to 0, this restriction is already there, and from first intersection of first, second and the third. So, we will get the solution as open interval 0 1. Now, similarly, let us simplify this one. So, we have x minus 1, x plus 1 greater than 0, that is minus 1, or you can put it on a number line. This one is minus 1, this one is 1, we have two factors. Now, in between 0 is there, so just put 0 here, we have negative into positive, negative in this interval. Since the roots are repeated odd number of times, so sign will be alternately positive and negative. So, I can put positive here and again positive here. What we are interested greater than 0. So, the interval will be minus infinity to minus 1 union 1 to infinity, the solution of this one. But we are interested in x less than 0. So, x less than 0, this part will be discarded and we have minus infinity to minus 1, because minus 1 is left to 0. So, we will get this interval. Hence, our solution will be minus infinity to minus 1 union 0 to 1. I can write set C as minus infinity to minus 1 union 0 to 1. Again, we will use the same technique. How to look at sets, whether this set is bounded above or not. So, this set is bounded above because one is, at least one of the upper bound is 1. This set is bounded above. I can write bounded above but not bounded below, bounded above but not bounded below. Okay. This set is bounded above but not bounded below. So, set of all upper bounds. So, since not bounded below, so we will not talk of infimum. Why? Because from completeness property of R, for existence of infimum, it has to be bounded below. So, we need and the set is non-empty. So, set of all lower bounds, sorry, set of all upper bounds. Set of all upper bounds bounded above, because 1 is alpha equal to 1 is one of its upper bound. Set of all upper bounds will be 1 to infinity, and supremum. Supremum is least upper bound of the set. So, least upper bound of the set C is 1, whereas this set is not bounded below. So, in this case we can see that the supremum exists because it is bounded above, but supremum 1 is not the member of the set. This is not the member of the set C. So, supremum may or may not belongs to the member of the set, and for existence of supremum the set has to be bounded above. Similarly, we can do the next part. Let us do one or two more questions on this. B part. Similarly, one can do this one, 5B part. Set B is given as collection of all those x belonging to set of real numbers such that x plus 2 is greater than equal to x square. Okay. So, let us simplify this x plus 2 greater than equal to x square. So, I can write this one as x square minus x minus 2 less than equal to 0. Simplify this one, we will get, factorize this one, x minus 2 into x plus 1 less than equal to 0. Since or we can see this one is also as a parabola. If we analyze this, x square minus x minus 2 equal to 0. So, this term, if we draw graphically, it represents parabola with the coefficient of x square is positive. So, it will be something like this, that it is going to cut at minus 2 x after putting x minus 2 equal to 0, we will get 2 and minus 1 minus 1. So, it will pass from minus 1 to 2, and we are interested in those portion which is less than equal to 0 below x axis. So, I will get its solution as minus 1 to 2, and since we have equality sign here, so I will get closed interval minus 1 to 2, closed interval minus 1 to 2. Now, I have already discussed how to compute this set. This set is already bounded above as well as bounded below. Another idea to check whether set is bounded below or not, if we are able to enclose any set into a length of finite interval, then this one is another approach to check whether a set is bounded or not. If we are able to enclose this set into a length of finite interval, then this set is bounded above. We will generalize this case in case of metric spaces. So, clearly every real number greater than equal to 2 is its upper bound, and every real number equal to 1 or less than minus 1 is its lower bound. So, from the collection of all upper bound, supremum will be 2 and infimum will be minus 1 in this case. Infimum will be minus 1 in this case. Let us do the remaining part. Okay. One more question is remaining, part D, 5D. Here D is given as collection of all those x belonging to R such that x square minus 2x minus 5 is less than 0. So, first of all we need to simplify this inequality, x square minus 2x minus 5. Assuming it as 0, first of all try to compute its root using the formula minus b plus minus root of b square minus 4ac by 2a. So, we will get, if I compare it with the standard equation ax square plus bx plus c equal to 0, then the roots are minus 2 plus minus root of b square, that is 4 minus 4 into 1 into minus 5, 4 into 1 into minus 5 upon 2. So, 2 get cancelled out, and within this within the square root we need to cancel by 4. So, it will be, let us do first it, minus 2 plus minus 4 5 20 24 24 upon 2 and cancel in the next step. So, it will be minus 1 plus minus root 6. So, one of the root is minus 1 minus 1 minus root 6, sorry 1 minus b plus minus. So, minus minus will be plus, sorry, here we have 1 plus minus root 6, this I need to correct here. So, one of the root is 1 minus root 6, 1 minus root 6, and another root is 1 plus root 6. Again this one is a parabola, and here we have strictly less than 0. So, this one is within this interval, or one can write that x belongs to 1 minus root 6 to 1 plus root 6. So, we know already how to compute supremum and infimum of such type of sets. So, every real number, this set is bounded above as well as bounded below, and set of all low upper bounds, set of all upper bounds, set of all upper bounds will be of this set of upper bounds of the set D, that is 1 plus root 6 to infinity, and from the set of all upper bound the least one is 1 plus root 6. So, I can directly write supremum as 1 plus root of 6. Similarly, with the same logic, 1 minus root 6 is one of its lower bound. Set of all lower bounds will be minus infinity to open interval minus infinity to 1 minus root 6 closed interval minus root 6, and from those lower bounds the greatest lower bound is 1 minus root of 6. So, we have completed this. The remaining questions, we will do more questions of such type using Archimedean property of R. Next we will learn about nested interval lemma and some questions based on this Archimedean property of real numbers, then representation of real numbers, and again we will come to the concept of countable uncountable set. We will do several results based on those representation and representation of real numbers into binary, ternary, decimal, etc. And we will show that how to discard whether the set is uncountable, whether the set is how to prove that a set is uncountable using method of contradiction. So, I will cover all these in the next topic. In the next lecture we will see some more examples based on this one. Remaining question you need to do as assignment from the book of Bartley. All these questions I am discussing from the book of R G Bartley. R G Bartley, exercise of R G Bartley and D R Sherbert.